In this video, we'll explore JAX for machine learning and learn how it enables fast, efficient computation with features like automatic differentiation and JIT compilation. We'll cover the basics, build a simple machine learning example, and see why JAX is becoming a popular choice for AI development. The first step is to import JAX, JAX NumPy, JNP, and NumPy, NP, so we can perform numerical computations and work with arrays throughout the project. Next, we create two JAX arrays, X and Y, containing floating point values. JAX arrays behave very similarly to NumPy arrays, making them easy to work with while also enabling powerful features such as automatic differentiation, just-in-time compilation, and hardware acceleration on GPUs and TPUs. These arrays will serve as the inputs for performing mathematical operations and demonstrating JAX's capabilities. Here, we compute the dot product of the two JAX arrays using JNP dot. The dot product multiplies corresponding elements from each array and then sums the results, producing a single value that measures how closely the two vectors are aligned. Finally, the result is printed to the console. We demonstrate JAX's functional array update using @set, which creates a new array instead of modifying the original one in place. We update the first element of X to 99.0, resulting in a new array called XUpdated while X remains unchanged, since JAX arrays are immutable by design. Finally, we print both the original and updated arrays to show the difference. In this section, we explore one of the most powerful features of JAX, automatic differentiation. We start by defining a simple function, squareX, which returns the square of its input. From this function, we use JAX grad to automatically create another function, grad square, which computes the derivative of the original function with respect to its input. This means we don't need to manually calculate calculus formulas. JAX handles it for us. When we evaluate this gradient function at x equals 3.0, it correctly returns 6.0, since the derivative of x2 is 2x2 times, and 23 equals 6, 23 equals 6. We then go a step further using JAX value and grad, which allows us to compute both the original function value and its gradient in a single call. This is useful in machine learning workflows, where we often need both the loss value and its gradients during training. By calling this function at x equals 3.0, we get both the value 9.0, since 32 equals 9, 32 equals 9, and the gradient 6.0. This combination of efficiency and simplicity is what makes JAX especially powerful for optimization and deep learning tasks. In this section, we explore one of JAX's most important performance features, JIT, just-in-time compilation. To demonstrate this, we define a function called slow matrix multiply, which repeatedly performs matrix multiplication inside a loop. While this operation is already computationally expensive, the repeated loop makes it even slower in standard Python execution, due to interpreter overhead and lack of optimization across operations. Next, we generate two large random matrices, A and B, using JAX's random number generator. These matrices are shaped 1000, 1000, making them large enough to highlight performance differences clearly. We then measure how long it takes to run our function normally using Python execution. This gives us a baseline performance time without any optimization. After that, we apply JAX JIT to our function, creating a compiled version called fast matrix multiply. JIT compilation allows JAX to transform the function into highly optimized machine code using XLA, accelerated linear algebra. The first time we run the JIT compiled function, it includes a compilation step, so it may not appear immediately faster. However, this compilation only happens once. When we run the function a second time, we see the real benefit of JIT compilation. The execution becomes significantly faster because the function has already been optimized and compiled for the hardware. This demonstrates how JAX can dramatically improve performance in numerical computing and machine learning workloads by removing Python overhead and executing optimized code directly on accelerators like GPUs or TPUs. After running the experiments, we can clearly compare the performance results. Without JIT compilation, The function takes about 0.032 seconds, reflecting the normal Python execution overhead. When we use JIT for the first run, the execution time is around 0.027 seconds, but this measurement still includes the one-time compilation cost, so it doesn't fully reflect the optimized speed. On the second run with JIT, the performance improves dramatically to about 0.0002 seconds, showing the true advantage of JAX's compilation system. This huge speedup happens because the function is already compiled into optimized machine code, allowing it to run extremely efficiently without repeated Python interpretation. In this section, we explore vectorization in JAX using vmap, one of the most powerful tools for writing efficient machine learning code. At its core, vmap allows us to automatically transform a function that works on a single input into a function that can operate on an entire batch of inputs, without requiring manual loops or complicated restructuring of the code. We begin by defining a simple function called predict singulate bias x, which represents a basic linear model. It takes a weight, a bias, and a single input value x, and computes the output using the equation wx plus bwx plus b. This is the same kind of computation used inside larger neural networks, but here it is kept simple so we can clearly focus on how vectorization works. Next, we define a single scalar weight and bias, w equals 2.0, b equals 1.0, along with a small batch of input values stored in a JAX array, 1.0, 2.0, 3.0. If we were using standard Python, we might process these values using a loop or list comprehension. While this would work, it would be inefficient because Python loops execute at the interpreter level and do not take advantage of low-level optimizations or parallel execution. As a result, performance can become a bottleneck when scaling to large datasets. To solve this, we use JAX vmap, which stands for vectorized map. This function automatically transforms our single input function into a batched version that operates efficiently over arrays. By setting an axes equals none, 0, we specify how each argument should be treated during vectorization. The weight and bias remain fixed and are reused for every computation, none, while the input array is mapped along its first dimension, 0. This tells JAX to apply the function independently to each element of the input array, but in a fully optimized way. What makes vmap especially powerful is that it does not simply loop in Python. Instead, it rewrites the computation so that it can be executed using JAX's underlying XLA compiler, which enables parallelism and hardware acceleration. This means that batching happens at a much lower level, closer to optimized C++ execution, rather than in Python. Finally, when we call batch predict with b inputs, we obtain the result 3, 5, 7, which corresponds to applying the linear function to each input value efficiently. This output demonstrates that all three inputs were processed in a single vectorized operation, rather than three separate function calls. In real machine learning systems, this kind of batching is essential for training neural networks efficiently, since it allows operations to scale smoothly to large datasets and high-dimensional tensors without sacrificing performance or code clarity. In conclusion, this walkthrough shows how JAX brings together speed, simplicity, and scalability for modern machine learning. We started with NumPy-like arrays, making it easy to work with familiar syntax while gaining access to powerful back-end optimizations. Then we saw how automatic differentiation removes the need for manual calculus by computing gradients directly from functions, which is essential for training models. With JIT compilation, we demonstrated how JAX can dramatically speed up execution by compiling Python functions into highly optimized machine code, reducing runtime from milliseconds to microseconds after the first run. Finally, using vmap, we saw how JAX eliminates explicit loops by automatically vectorizing operations, making batch processing both cleaner and significantly more efficient. Together, these features make JAX a strong tool for building fast, scalable, and research-friendly machine learning systems.